All right, hi everybody. Mrs. Pesic here. We are finishing up section 2.5. 2.5, as you know, was zeros of polynomials, and last time we did talk about Descartes' rule of signs, and that is a way of testing how many positive real zeros we're going to have and how many negative real zeros we're going to have, and that would allow you to do, if you had that, I hope that you've already done numbers A and B from number 5 on the gift. With number 5, that turned out to have 3 or 1 positive real zero, and it ended up having no negative real zeros. All right, and then for B, as a check, I hope that you've done this one. If not, maybe you'll do it with me. F of x itself has how many sign changes? Well, it goes from negative to positive, so that's one sign change, and it stays positive, so there's only one sign change. So f of x has one positive real zero. All right, what about the negative real zeros? Let's look at f of negative x. That's going to be negative 3 times negative x cubed plus 2 times a negative x plus 1. Negative 3 times negative x times negative x times negative x is going to be the same as opposite of x cubed. So this is actually going to be a positive 3x cubed. And then this is going to be a minus 2x and then the plus 1. So as we can see here, it goes from positive to negative. And that's one sign change, and the negative to positive is the second sign change. So there's going to be 2 or 0 negative real zeros. So we either have 2 of them or we have none of them. All right, that's what the Descartes rule of signs says for the possible number of real zeros. All right, moving on to the upper bound and lower bound test. This would be another way of determining, you know, how we doing on finding zeros, that kind of thing. So let's say let f of x be a polynomial function with real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division. Well, if c is greater than 0 and each number in the last row of your synthetic division process is either positive or 0, then C is an upper bound for the real zeros of f. What does that mean? If it's an upper bound for the real zeros, that means there will be no real zeros higher than C. All right, so that was another way that people would be able to tell whether they were done looking for zeros or, you know, could there be more zeros further to the right and so on. Well, here's a way of testing whether there are any more zeros further to the left. If C is less than 0 and the numbers in the last row of your synthetic division process are alternately positive and negative. By the way, I put this already. I hope you're not writing this down because this is already on your gift. The 0 entries count as positive or negative. Then C is a lower bound for the real zeros of f, and there will be no real zeros less than C. So let's take a look at this example. We're supposed to be finding the zeros of the function. Start by considering the rational zeros. This is number 6 from your gift. All right, so if I'm going to call this part A, finding the possible rational zeros. All right, that is where you do the P over Q list. So we need P over Q, where the P values are going to be the factors of your constant term. So that's just going to be plus or minus 1, plus or minus 3. And the Q values are going to be the factors of your leading coefficient. So here's the P's over here, Q's over here. So we want all the factors of 8. That's plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So when we list our P over Q values, that's going to be 1 over 1, 3 over 1, 1 over 2, 3 over 2, 1 over 4, 3 over 4, and 1 over 8, and 3 over 8. All All right, so we don't want to have to test all of these, but before we look at the graph, let's at least see about the Descartes rule of signs. How many real zeros should we be looking for? So in that case, if I look at this, I'll call this part B. Here's my function again, f of x equaling 8x cubed minus 4x squared plus 6x minus 3. And if we look at Descartes' rule of signs, all right, we notice that there's one sign change here, two sign changes because it goes from positive to negative, then negative to positive, and then back to negative. So there are 3 or 1 positive real zeros. They may be rational or they may be irrational, but there are 3 or 1 of them. To find the number of negatives, we need to look at f of negative x. And with this, if it's an odd exponent, it will change sign. So negative x cubed, negative 8x cubed. If it's an even exponent, it will not change sign. So that's going to stay a minus, this is going to stay a minus 4x squared. And then this one is to an odd power, that's 6x to the 1. So that's going to change sign to a negative 6x, and then the minus 3 is staying the same. I got all of this from, don't forget where this is coming from. This is all coming from me plugging in negative x wherever I saw an x in the original function. All right, when we do that, we should get this new answer here. Well, how many sign changes are there? Wow, none. Because there are no sign changes, that means there's no negative real zeros. All right. All right, so then what about the upper and lower bound test to help narrow down our search? Well, if we're going to do the upper bound test on our function, I'll call this part C. Let me get the function written again. If I'm going to do the upper and lower bound test, let's see, I've got, you know, where's my list of zeros? This is my list of, not list of zeros, but my list of possible rational zeros. Let's say I wanted to try positive 1. Let's see if we can knock out any possibilities lower than 1. So I would put 1 in the box, and my coefficients are here. And if I do synthetic division here, bring down the 8, multiply, I get 8. Here I get 4, multiply 4, add, I get 10, multiply, I get 10, add, I get 7. Now, sure, we don't have a 0 as our, you know, as our remainder here, but that's not what we're really looking at. In the upper bound test, we want to know, let's go back to the upper bound test. Upper bound says if each number in the last row is either positive or 0, then that number C is an upper bound for the real zeros. All right, that's what we have going on here. We've got every number here. These numbers are all positive or 0, right? So 1 is an upper bound for the zeros. That means I don't need to try, you know, any of the numbers that are higher than 1. So I know it's not going to be positive 3. I know it's not going to be, you know, 3 halves, and so forth. So I can just eliminate those. And not only that, there's not going to be, it's not going to be like a 4.6932 either. It's not going to be anything to the right of 1. 1 is an upper bound. All right, what about testing negative 1 to see if that's a lower bound? So if I put negative 1 in the box, and I'm going to divide this with 8, negative 4, 6, negative 3 again are my numbers. I bring down the 8, multiply, I get negative 8, add, I get negative 12, multiply, I get positive 12, add, I get 18, multiply, I get negative 18, add, I get negative 21. So that means, if you notice, these are alternating positive, negative, positive, negative, positive, negative. Since they alternate, that means that negative 1 is a lower bound for the zeros, for the real zeros. That means I will not have any zeros to the left of -1 on the x-axis. Let's take a look at the graph to see how we are doing with this. But you see, if that is true, then we don't have to test a bunch of those numbers. Let's type this in. This graph, go ahead and do this on your calculator if you have not already. 8x raised to the third minus 4x squared plus 6x minus 3. There's our graph. Sure enough, it's got kind of a strange shape, but we see, yeah, 1 is an upper bound for the zeros because we see no zeros to the right of 1. Here's 1. There's no zeros to the right of 1. And -1 is a lower bound because there's no zeros to the left of -1. So 1 is an upper bound for the zeros, -1 is a lower bound for the zeros, and that means any zero that we have is going to be in between -1 and 1 based on the numbers that we chose. So back to this for a minute. If we are trying to find then the zeros for this function, I know that it's not going to be, it's not -1 or 1. I know it's not going to be +3 or -3 because 3 is to the right of 1. That's no good. -3 is to the left of -1. That's going to be no good. +1/2 has potential, but not the -1/2. +3/2, -3/2, no good because they're, again, outside of our boundaries, right? We know it's not going to be to the right of 1 or to the left of -1. 1/4 has possibilities, but not -1/4. And again, remember, I know not to look for any of the negatives, right? Where was my, right here. No, there's 0, negative real 0. So I don't even have to consider any of the negatives. So I'm going to scribble out the negatives right now because of that Descartes' rule of signs. 3/4 has possibilities, 1/8 has possibilities, 3/8 has possibilities. So now that we know that, let's go back to the graph and see if we can narrow this down. Is there a rational zero? Well, let's try 1/2. Menu, trace, graph trace. If I try 1/2 or 0.5, sure enough, that is a zero, is 0.5. All right, and we're supposed to find all the real zeros. So at this point with this problem, I would ask you to put 1/2 in the box. And you're going to put your coefficients, which are 8, -4, 6, -3. And when we do this synthetic division, I bring down the 8, multiply, I get 4, add, I get 0, multiply, I get 0, add, I get 6, multiply, I get 3, add, I get 0. So 1/2 does work. Not only that, I'm left with this. These are the coefficients of my quotient when I'm dividing. So my function could be written as x minus 1/2 times 8x squared plus 6. There's no x to the first term, right? This is x to the 0, x to the first, x to the second. So to find the remaining zeros, I can set both of these equal to 0. Remember, we only saw the graph crossing through the x-axis in one place. That's right here. So we think that the other two zeros are going to be what? Imaginary, right? So let's solve this and see if that's true. We get 8x squared plus 6 equals 0. 8x squared equaling -6. So x squared equaling -6/8 or -3/4. And then we take the square root of both sides. Don't forget that plus or minus. And we get x equaling plus or minus square root of -3 over square root of 4. That's going to be plus or minus I times the square root of 3 over 2. And so I think that when we make our list of zeros, we would say the zeros are 1/2, I rad 3 over 2, and -I rad 3 over 2. So we had 1 real and 2 imaginary zeros. All right, as you can see on your gift, there are 3 more hints for finding zeros. You should See if I have them. Here they are. Always look for common factors first. All right. Then second tip is to try to get down to a quadratic factor. And then you can use quadratic formula to find the remaining zeros. And the third tip is that the complex zeros come in conjugate pairs. So you know that, for example, in that last case, we had square root of I times square root of 3 over 2, and its conjugate would be negative I times the square root of 3 over 2, right? Think of it as 0 plus and 0 minus, right? So conjugate pairs. So if 2 plus 3i is a 0, then 2 minus 3i is also a 0. All right. Okay, so let's take a look at this example. Find all the zeros of the function and write the polynomial as a product of linear factors. So again, if we go through the drill here, if we start by listing your possible P over Qs, that's going to be plus or minus 1, plus or minus, not 3. What goes into 35? 5, 7, and 35. And then really my Q values are the factors of my leading coefficient. Well, that's just plus or minus 1. So that's really just going to be not even necessary to include. So that's going to be my whole list of P over Q values. And so I could start trying them randomly, but let's check for how many positive real zeros and how many negative real zeros there will be by doing Descartes' rule of signs. So, for example, if we look at the sign changes, I see it starts out positive, but it stays positive, stays positive, stays positive. What does that tell us? It tells us that there are no positive real zeros. It's never going to cross the x-axis to the right of the y-axis. All right, and that was because there were no sign changes in f of x. All right, then to find the number of negative real, so by the way, that means I can eliminate the positive here, positive here, positive. I don't even have to try those. All right, because there's going to be no positive real zeros. So that means there's going to be no positive rational zeros. What about the negatives? If we look at f of negative x, that's negative x quantity cubed plus 9 times negative x squared plus 27 times negative x plus 35. And that means that we're going to have opposite of x cubed because that sign changes for a degree that is odd. All right, so it changes sign, and then from the original, I should say. And then here, the sign is not going to change, so started at 9x squared, it's going to stay 9x squared. The 27x is going to change to a negative 27x plus 35. So how many sign changes do we have in f of negative x? Well, it starts out positive, goes to negative. No, starts out negative, goes to positive, that's 1. Changes back to negative, that's 2. Changes back to positive, that's 3. So there are 3 or 1 negative real zeros. All right. And if we wanted to see whether there was a, let's say if there was a lower bound, if we try and use the upper and lower bound test, I know I don't have to try any upper bounds because there's no positive real zeros. But there may be 3 or 1 negative real zeros. Well, there will be 3 or 1 negative real zeros. So let's pick a number from our list. Let's say negative 5, for example. It's a negative 5 there. So let's try negative 5 and see if that's going to be a lower bound. So I need my coefficients not from f of negative x, but from the original function. So that means I need 1, 9, 27, and 35. So if I try and do this here, you know what? Maybe I'm just going to not. Negative 5 is going to be, the numbers are going to be too big for me to do on this video because I'm not holding a calculator. You guys are though, so you could try it. But I'll try negative 1. So I bring down the 1, multiply, and I get negative 1. Add, I get 8. Multiply, I get negative 8. Add, I get 19. Multiply, and I get negative 19. Add, and I get, 35 plus negative 19. Borrowing, subtracting. I get 16. And that's positive. So that means what? That negative 1, is that going to be a lower bound? So is negative 1 a lower bound? And the answer is no, because the numbers here in our last row, because last row is not alternating. Remember, they have to alternate positive, negative for it to be a lower bound. That tells me, I don't know what that beeping noise is, but that tells me that negative 1 is not a lower bound and that the graph is going to cross to the left of negative 1. Let's pull up the graph and see how we're doing with this. Let's see. All right, so we're trying x to the third plus 9x squared plus 27x plus 35. All right, there's our graph. Sure enough, it looks like there is 1 0 for the negative zeros. I don't think I see any more over here. And not only that, it looks like it might actually be occurring at negative 5. So if I had tried negative 5, I might have been rewarded by getting a 0. Let's test it here. Menu, trace, graph trace. If I type in negative 5, sure enough, it is a 0. So negative 5 is going to be a 0. It looks like it's the only one. So I bet there's two imaginary zeros that you can find by doing synthetic division. So I'll let you finish up that problem. And I'm going to stop this video at this time, and hopefully you can complete the rest of this gift and the problems from the 2.5b assignment. So I will expect 2.5a and 2.5b homework completed the day we meet after the test. So not due on test day. All right, that's it for me for right now. Have a great day.